Hello, pre-calculus students. In our last lesson, we learned some fundamental trig identities. In this lesson, which is really fun if you like algebra, we're going to be using those fundamental identities to prove some other ones. So in this case, we're going to be verifying trig identities. When we say verify, that means I'm telling you it's true. You just have to prove it. There are some guidelines on page 357 of our current text. The first one, we're going to change a bit. It says work with one side of the equation at a time. When you verify trig identities, you change only one side of the equation in all of your process. In other words, if you're going to change the right side of the equation, you don't touch the left side ever. That way you're turning the right side of the equation into the left side, or you're going to turn the left side in to show that it's equal to the right side. You don't change both of them to show they're both equal to something else. And I will agree that it's better to work with the more complicated side. In other words, change the more difficult, the more complex side into the easier side. Look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. Look for opportunities to use those fundamental identities that we learned in the last section. Note which functions are in the final expression you want. If you're trying to get something with cosines in it, because that's what your final expression is, then look for ways to get cosine in there. Sines and cosines pair up well, as do secants and tangents, and cosecants and cotangents. As a last resort, some people want to do this first, but I'm telling you, as a last resort, if those other things don't help, try converting everything to sines and cosines. See if that helps. Then I like number 5. Always try something. Even making an attempt that leads to a dead end can provide insight. So identities are something, a lot of times we believe identities are expressions that are always true. Not quite. They're true wherever the functions are defined. For instance, we know that this is true. So if we divide both sides by a minus b, we would get this. And could we say that we know that this is an identity? This is true no matter what the values of a and b are. But is this always true? And the answer is no. If a equals b, then a minus b is 0. And you'd have 0 divided by 0. That's an indeterminate critter. We're not even going to go there. So identities are true everywhere the function is defined. So here's a problem on page 358. I think I did it differently. Yep. So they did it one way on page 358. I'm doing it another way. So I just want to show that this is equal to 1. So I'm not even going to mess with the right side. This is obviously the more complex side of the problem, and that's what I want to change. And I want to get everything equal to 1. So the first thing I notice is that sine squared theta plus cosine squared theta. That's one of our fundamental identities. That's 1. Okay, I'm getting closer. Now, I don't see any other option but to replace this with 1 over cosine squared theta. And then you see the cosine squared thetas cancel to get 1. And now I've shown that this left side is 1, which is equal to the right side. And I put a check mark over that equal sign saying, yep, I'm done. So in these types of problems, we're combining our algebra knowledge, manipulating expressions, and our trig knowledge. We needed this fundamental identity to get here, and this fundamental identity to get here. Excuse me. Here's the second problem on page 358 of our current textbook. we want to show that this 2 times the cosine squared of beta is equal to this plus this. Well, my rule of thumb is I'm looking at this, I'm seeing 2 fractions. I need to get 1 term over here. And obviously this is the more difficult side. So I can't do with 2 terms. I need to get to 1 term. So I need to get a common denominator here. That way I can make all of this 1 term, and then I'll see if I can make it equal to this. So I multiply this expression by 1 plus cosine beta over 1 plus cosine beta, and this one by 1 minus cosine beta over 1 minus cosine beta. Then when I add them, the cosine betas cancel, and I'm left with 2 over, and then I FOIL this, and that's an a minus b times a plus b. Again, this is where your factoring knowledge is just so critical. You should recognize that as a minus b times a plus b. That's going to be a squared minus b squared. And then, whenever you see a 1 and a sine squared or a 1 and a cosine squared, see if you can use the Pythagorean identity. And sure enough, we can. If sine squared theta or sine squared beta plus cosine squared beta equals 1, subtract that cosine squared beta, and you get 1 minus cosine squared beta equals sine squared beta. And then 1 over sine squared beta is cosecant squared beta. And it checks. So this is true. This, again, we said verify the trig identity. So we're telling you it's true. You just have to prove it, and we did. The catch is it's not true everywhere, because it's not true where cosine beta equals 1 or negative 1, because then these terms aren't even defined. Again, I want to point out, top left of page 361, they manipulated both sides of the equation. Don't do that. Change only one side of the equation. So here's a problem I tried to do. Here's an interesting identity. Sometimes people want to cross multiply. Well, when you cross multiply, you're changing both sides of the equation. So you can't do that. So what I did is I multiplied both sides I multiplied this left side by sine theta over sine theta. And then I got cotangent squared theta is cosine squared theta over sine squared theta. So with those, one of those signs canceled out, I got cosine squared theta over sine theta. I'm not getting anywhere closer to this. So I tried it, it didn't work. That was step 5 on page, what was it, 357? Try something. This didn't work. So we had to try something else. And what I did here is I replaced cotangent squared theta with cosecant squared theta minus 1. If you're not sure where that came from, look at the 3 Pythagorean identities. The first one obviously is sine squared theta plus cosine squared theta equals 1. Look at the other 2. And I will tell you that I can't find them right now. Oh, there they are. Page 350. If you take sine squared theta plus cosine squared theta equals 1 and divide all 3 terms by sine squared theta, you get a second Pythagorean identity. And if you go back to the original and divide all 3 terms by cosine squared theta, you get a third Pythagorean identity. So I made this substitution here. And then I call this cosecant theta plus 1. That was a mistake. Well, this is an a squared minus b squared. So I should be able to factor that to a plus b times a minus b. Notice I'm not even writing the right-hand side of the equation because I don't want to touch it. These will cancel. So now I'm just left with this. All right. I'm kind of stuck, so I'm just going to make this 1 over sine theta. And then I see I need a 1 minus sine. Oh, look at that, sine theta over sine theta I know is 1. So I'm going to replace this 1 by sine theta over sine theta. Now I've proven the identity. So what I want you to get out of this is, one, the importance of your algebra skills, especially factoring. You can't get away from that. And second, your knowledge of those fundamental identities. You should recognize that, when you see a cotangent squared, you can find that in a Pythagorean identity. Same with a cosecant squared, or a tangent squared and a secant squared. All of those you can find. In fact, all 6 of our trig functions will appear in one of the 3 Pythagorean identities. Also, the idea of factoring, rewriting expressions as I went from 1 to sine theta over sine theta. All of these are techniques. There's no way to do this without doing it. So what I would recommend is that you try some of these problems in the textbook, especially the odd numbered ones. Look in the back of the book, make sure the answer's there, then try some, make sure that you can do them. Now in our current textbook, here's another one. Sine to the 4th alpha, sine squared alpha minus sine to the 4th alpha equals cosine squared alpha minus cosine to the 4th alpha. Neither side is more difficult than the other here, so I just chose to change the left. I factored a sine squared out, and instantly I see a sine squared. I know that there's a 1 here, totally a Pythagorean identity. Sine squared theta, Pythagorean identity. And now the problem is solved. There isn't just one correct way to do these types of problems. Here's another one. I recognize that sine squared theta is 1 minus alpha is 1 minus cosine squared alpha. And if that's sine to the 4th, that's sine squared squared, or 1 minus cosine squared alpha squared. Foil this. Distribute the -1 out in front of here, and you'll notice that these 2 1s canceled, and you get a negative cosine squared alpha plus 2 cosine squared alpha, that's 1 cosine squared alpha, minus cosine of the 4th alpha, and I've completed my verification. So I've done the same problem 2 different ways. Here's number 17. Maybe after you watch this video and you've taken your notes and we've had class and you're not, you don't have these things memorized, maybe you try to do numbers 16 and 17 on page 362, knowing that I've already worked them out for you. Also look in the back of the book. Practice, practice, practice. As the old guy said, there is no royal road to geometry. In other words, there's no cheat sheet. You got to just do it. Do the practice. So anyway, here is our identity. And I determined that this side was the more difficult side. One, because it has a fraction. Another one, because there's a secant in it. All right, so tangent squared, the secant squared theta minus 1, again, comes from one of the Pythagorean identities. I highly recommend that you study those Pythagorean identities. Start with the first one and derive the other two. Become very familiar with those. All right, secant squared divided by secant is secant. 1 over secant theta is here. That's 1 over cosine. That's cosine theta. Then what I did is I said cosine theta, I could to get a common denominator, because I only have one term over here. So I need to combine these. So I multiplied this by cosine theta over cosine theta. And that's where this cosine squared theta came from. 1 minus cosine squared theta is sine squared theta. Now, if I make that sine theta times sine theta over cosine theta, I've solved, or I've verified the identity. So I've given you the guidelines from the book. That was page 357, I pretty much believe. I've given you some example problems. I've shown you that you can solve problems different ways, as long as your math is correct. I've also shown you the requirement to change only one side. I know your book says change one side at a time. More rigorous math books say you get to only change one side. So that's what we're going to do. And this is really going to be a good practice of your algebra knowledge. When students bomb calculus, it's usually because of bad algebra skills. It's not that they can't do the calculus, it's that they keep screwing up the algebra, and algebra is so important. You take algebra, some geometry, a lot of trigonometry, mix it all together in one problem, you get calculus. So that's why the algebra is so important. So here we are combining algebra and trig together in order to help you succeed in an actual calculus course. So that's all I have for you for this lesson. Have a great day.